All right, so why don't you guys get started? There is a little problem here with a function that takes a function as a value. See if you can trace through running apply n with +2 and 2 being the arguments. All right, so you've had a couple of minutes to think about this particular problem, and it's a very small function, and yet this is a little bit involved. So we start off, and I'm going to short form a lot of this because I don't want to write that much. So we're just going to call it app for short. And our arguments are the plus operator, 2 and 2. Remember that you can pass functions as arguments because functions are actually first-class values, which means you can do anything with a function that you would do with a number or a string or anything like that. It's a regular value. So, basic substitution rules for a function. And we have no local to deal with here, so we can just substitute it right in. There's some number of closing brackets there. I'll let you figure it out. All right. So now we're going to check if 2 is 0. Now we all know 2 is not 0. So I'm going to avoid writing some of this. All right. False. So we drop it. And then the else always evaluates to true, so we're just going to replace that with the body. There we go. Now, it's not quite time to do our recursive application yet because that function has an argument that hasn't been evaluated into a value. So we've got to evaluate sub12 first. Which, of course, subtracting 1 from 2 is going to give you 1. And now we can actually do our recursive application here. So replacing plus 2 and 1 into the body. And now we have to check if 1 is 0 again. Else always evaluates to true, so now we're going to go back up here. And we've got we evaluate the sub 1, 1, which is going to give us 0. And now we got one more recursive application. Now this time, 0 is 0, right? There we go. All done. Any questions? It's not too bad, right? Remember that because a function is a first-class value, you can pass it in as an argument. And then inside you can apply it if you so choose, or you can just pass it forward. It can be the thing that you carry along with you. All right, then if you have a clicker, please do get it out. All right. I will give you a minute for this. All right, so If you haven't clicked in, you should do so now. All right, let's see where everybody sits. Most of you said A. A is correct. Filter consumes a predicate and a list, and it is going to apply that predicate to each element of that list. And for elements of the list where the predicate produces true, that gets kept, and anything that produces false gets tossed out. It's great, right? Filter's a great function. All right, so let's do something harder, right? Now, if you're smart, you're sitting there with a computer out and typing this into bracket. All right, get your answer in. I'm going to shut it off right now. So, most of you said B. B is the answer. The predicate number is going to produce true if the list element is a number. And in our list here, we have 5, which is a number, hello, which is a string, said, which is a symbol, and 0, which is a number, and the empty list, which is a list. So, only 5 and 0 pass the test. Yeah? No, because when you have a quoted list, the quote gets applied to everything inside. So if you have a plus operator in a quoted list, it actually turns into the symbol plus. Yeah.
So how can we put constants in a quoted list?
You don't.
We can.
Be careful with quoting. Quoting can do bad things if you're not paying attention. I know writing the word list is a pain in the ass, but it's the safest, because then what you put in the list actually means. We'll do an example with this later. All right, one more, and you get 2 minutes for it. got about 15 seconds to get to your answer. Remember, even a wrong answer gets you a point, so. All right, so let's see where everybody falls on this one. Very good. Most of you got it right. It's A. So this was a particularly nasty little piece of code. What I've done is I've made the predicate be the result of a local that produces a function. And inside the local, I define x to be 5, and then I have a function gt whose argument is also x. And then inside the body of gt, we check if x is, or 3 is less than x. Now, which x is, that is going to be the argument x, not the constant x, because we always choose the meaning for something to be what is defined in that scope. So if you have defined x in your scope, then you will take that value of x. So 4, 5, 6, 7, 8, 9, 10 are all the numbers in that list that are bigger than 3. Yeah. And if you're sitting there thinking, oh, that's a sneaky one, you haven't seen my OS exams. It is not beyond me, and I'm sure you might have seen it on Reddit, to make all the true-false answers all the same. Or the TF pattern, and you're sitting there scratching your head like, this can't be it. I must have something wrong. Nope. I like to be sneaky. All right, now, since the other class got this one free, I'm going to let you have 15 seconds to push the answer. Got to make it fair, right? All right. Cool shit that Racket can do. That's not so fun to do in any other language. So we've looked at the fact that functions are actually first-class values. That means that they can be passed as an argument to a function. They can be produced by another function. You can bind them to identifiers, and you can even do things like store them in a list or a structure because they're just a value, and you can treat them like any other value. And by having this ability, there's lots of really cool things that we can do. For example, we had that function eat apples and keep odds. And these two functions, actually, that's kind of cool. You see that? Look at that. I'm switching between them really rapidly. You notice the only thing that's changing here is the name of the function and the predicate we are using to determine, can I keep this in the list or not? What that is a really good example of is the fact that these two functions, even though they are removing different things from the list and they are working on a list of a different type, they're actually the same function. And whenever you see this kind of behavior, you realize I can abstract this. I can make a function that consumes the predicate as an argument and then implements it once, and it will work for everything. And in fact, that function is called filter, and it's built into Racket, and you don't have to do anything because it's there. But here's our implementation of it. And of course, it looks just like keep odds and just like eat apples. It's going to say, if the list is empty, produce empty. Otherwise, if the predicate produces true, then keep the item. Otherwise, don't. Same thing. And filter is a very powerful function. It's very powerful. We have gone, so we're going to implement this once. And of course, since we're using Racket, filter is already implemented for you, so you don't have to implement it at all. And now, in order for me to write the function eat apples or keep odds, well, I just have to call filter. So I've redefined eat apples because I still wanted that named function. Now I'm just going to call eat apples is just filtering things that are apples from or things that are not apples from my list, and that's it. So you go from having thousands of lines of repeated code to a single implementation that's called everywhere else. And then if there's a bug in your code, you fix it in one place and it fixes everything, which is great. That makes your code easy to maintain. It makes it very reusable because that one function can be reused many, 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 many times. And now, instead of having, all of this tens of thousands of lines of code, you've got like 10. We like that. I don't like it when you open up somebody's code and they've got like thousands of lines of code. I have written programs that are over 25,000 lines of code. It's a pain. And you are always looking at where can I abstract this code to simplify it so there's fewer lines, more reusable. And this is pretty powerful. Then we left off, we were actually talking about the ability to produce a function. So we had this lovely little thing called makeAdder. And you could think of it almost as like a little function factory. Because inside of makeAdder, you passed it n, and it produces a function that added n to whatever you passed to it. It built you a function. So instead of having to make add 1 and add 2 and add 3 and having to actually implement it fully for each and every single version, which admittedly for this is really easy, but you can imagine more complicated cases, you just create this little function factory where you pass it the base argument and it spits out a new function for you that does what you want and you can use it. Now, of course, what's the name of that function? So it's kind of weird to use because if you look at how we were using it, I want to go back here. makeAdder 3 produces a function that adds 3, and then we want to use that function to add 4 to 3. That's really awkward. What I really want to do is then bind the function produced by makeAdder to the name I actually want. And so we can do that because we can bind names to functions, because functions are values. So for add2, I just call makeAdder2. makeAdder2 builds the function, and then I bind it to the name add2. And then for add3, I call makeAdder3, and it produces a function that adds 3, and I bind it to the name add3. And the same for 7 and 8 and whatever you want. Admittedly, this is a really simple function, so maybe you wouldn't do this here. But. All right. How do you actually trace through this, though? So we start off with, we have add2 is bound to makeAdder2. Well, that means that the name add2 is bound to an expression. And before we can actually call add2, this is what we're evaluating right here, by the way. Before I can add 2 to 3, I actually, need to do some work. So first off, when I do add2, makeAdder2, we're going to evaluate that. So I'm going to take makeAdder2. The argument is a value, so I substitute it into the body. So add2 is now bound to local define fm plus 2m produces f. Okay? We still don't have an evaluated expression here. So we go to the next step, and that is dealing with the local. So we take function f, and we're going to rename it to something unique. And in a single step, we rename it, rename all the uses of it within local's body, lift it out into the global scope, and drop the local, leaving with the expression. So you see here, we've got the renamed F43 is what we've called it because we picked a random number. And then I have lifted it out. And then in define add3, I am replacing where the function was with what the body expression of the local was, which is just F43, the thing we just lifted out. So now that constant is all defined and ready to go. I've bound a name to a value. Now when I call add2, what happens? Well, add2 is a constant, so I'm going to have to look it up, and I replace it with F43. Oh, now we actually have our proper function here, and so, its argument is a value, so we use regular function substitution rules, substitute the 3 into the body of F43, we get 2 plus 3 gives you 5. There were no special rules here at all. We didn't have to introduce anything because there's nothing to introduce. It's fairly straightforward. Basic rules. All right. So let's do something more fun with it, right? So you might remember we were talking about an arithmetic expression tree. And that was for those operators that consume more than 2 arguments. So in bracket, plus and multiply can actually consume any number of arguments. And so we created this tree where nodes can have any number of children. And we represent the children as a list. And so each node has an operator represented by the symbol plus or the symbol multiply, and then the children is a list of arithmetic expressions, which may be a number or a node. And if it's a number, it's a leaf, and if it's a node, it's an internal one. And then you can really see here a few examples of us actually using it. So this here is an arithmetic expression, because if you look at the data definition, a number is an arithmetic expression. If you evaluate 3, I should hope you get 3. Otherwise, it wouldn't make sense. And then if I have an arithmetic expression as a single node, with plus being our operator, and then 2, 3, and 4 being our children, we would expect that, of course, to add up to 9. And if we give plus with an empty list, interestingly enough, you might think that the plus operator in bracket, if you give it no arguments, gives you an error. It doesn't. If you put plus in brackets by itself, you get 0. That's kind of cool. That's going to be useful, by the way. So when we implemented this, and this is going back a few modules, we had this mutually recursive function where eval, which is the function we want our user to see, is going to say if it's a number, just give the number. And if it's not a number, i.e. it's a node, then we need to apply the operator of this node to our list of children. And so we called this myApply function, which if it's empty, we produce the base case that's appropriate for the symbol, which has this nasty nested contour. Nobody likes that. I certainly don't. And then we check, is this operator a plus? Okay then, we'll apply plus. Otherwise, apply multiply. I do not like this code at all, because having your operator as a symbol seems really, really silly to me, because we have to do all this extra work to figure out, is the symbol a plus? Okay, then add them together. And if you would just pass the operator in as an operator, then we wouldn't have had to do all that junk. So, let's do that then. So, same structure as before, but the data type is going to be a little bit different. The operator is no longer going to be a symbol. It is now just going to be the damn operator, a function as a value. And you can see here there's not much difference in how we specify it. We just don't put the quote in front of it. You're done. All right. Now, as I said before, one last observation before I show you the implementation here. Plus with no arguments gives you 0. Multiply with no arguments gives you 1. I'd like to point out that these are the base cases. Which means that myApply is about to become real simple. So, at the top, we have the old version of myApply with a bunch of simple comparisons and a nested con. Ugly. And here's our new version. 4 beautiful lines. If empty, apply the operator to no arguments. Otherwise, apply the operator to evaluating the first child and the rest of the children. Done. Wrapper doesn't have to change. It's beautiful, isn't it? Now, if you want to make it even prettier, you're going to take that myApply and you're going to shove it inside a local in the wrapper, and now you're down to 1 function. That's right, too. Okay. I've already shown you how to do this for the binary expression tree. You're welcome to play with it again. But what if instead of using a structure, what if we, for the nodes, what if we used a list? So before what we did was we were doing make AI node plus, and then we passed in our list of children. But you know, I don't like typing all that structure code. I can just represent trees as embedded lists, which, by the way, you're going to be doing on assignment 8. since I'm really, really lazy and I don't like typing out lists, I'm going to be very tempted then to use the quote notation. Here's the problem. When you see this quote notation here, the quote actually gets applied to everything inside, which means we are going to turn this plus operator back into a symbol. Oops. Okay. So maybe we do want to handle our operators as being symbols. What would we do? Okay. So what we're going to do is we need to be able to take the symbols and turn them into their proper operators. So we can create an association list where the key is the symbol and the value is the actual function. And then what we're going to do, so we have our translation table here, we need a lookup function. And so our lookup function is going to be, if this association list is empty, we produce false. Otherwise, we are going to compare this key to the current one, and if they're equal, we produce the second one. Otherwise, we keep looking. It's pretty cool, right? All right. So we have our translation table, an association list, effectively, mapping symbols to operators, and we have a lookup function. And we can use this to make our original code actually work where the operator is still a symbol. And what's interesting about this is, yes, we've changed this a little bit because we no longer actually are using structures. We're now using a tree represented as nested lists. But other than that, my apply hasn't changed. The base case is still applying the operator to no arguments. Otherwise, applying the operator to evaluating the first argument and the rest of the arguments. It's the same. The only difference we had to make is to eval. And now when I pass the operator into my apply, we're going to do a lookup in our translation table. Okay. Still pretty tight. Now, if you were to ask me which of these two implementations do I prefer, the first one, not the one from Module 11, but the one where we're actually going to use the operator in the list and not the symbol. I find this use of the translation table to go between the symbol and the actual function to be very awkward, because that translation table has to live somewhere, and that lookup function has to live somewhere, and presumably a few functions are going to need it. And it seems like a lot of code I have to create and edit. When, you know what? I'd rather just tell my user, hey, can you not use quoted lists, please? I'd rather do it the other way. But to each their own. Programmers rarely agree with each other, by the way. All right. So you've seen all of the uses now for our beautiful functions as first-class values. And we're not done. Because there's still some stuff we haven't talked about, and that is the contract. If you actually go back to this, anywhere where there's a contract where we pass the operator in, you may notice that we left it as op or question marks. Op, which is the name of the argument, is not a type. That's the name of the argument. So what is the type? Actually, it's easy. The type of a function is the contract of said function. That's it. Now, you don't need the name. So you might be thinking I have to put, for the greater than symbol, you don't put greater than, colon, num produces bool. You just need the part that shows arguments produce value. So num produces bool, that's all you need. Put it in brackets, and you're done. So if we look at our association list for the translation table of symbols, our elements of the association list are two-element lists. The first element is a symbol, so we say list sim, and the value is actually a function. And these are arithmetic functions. They are binary expressions, so they consume two numbers and they produce a number. So I'm saying that the elements of my association list are list sim, num produces num. And then, since the association list can have multiple key value pairs, we have a list of those. And then if you look at the value that's produced by lookup, since the symbol may not be in the table, we need to give an indication of that happening. So we'll produce false if the symbol's not in the table, and we'll produce the operator otherwise. So the value produced by lookup is going to be false, or the contract of the function, which would be num produces bool. And note here how we're using any of false as the function contract. Now it's very tempting to do any of bool, but that's not accurate, because under no circumstance would this function ever produce true. And you should always make your contracts as precise as possible, because if you don't, then you can't anticipate that your user will know how to use it properly. And if you're trying to use somebody else's code and they just say bool, then you're going to assume that you have to consider both the true and the false and the function case, when simply it's not possible for the function to produce true. So make them precise. Yes?
So the function produces only one of two booleans, and we disregard the contract in the contract.
Yeah, so instead, let's say, let's make a function that for some reason asks if 0 is 0. That function always produces true. So you could have a function that consumes a number and then doesn't do anything with it. So it says num produces true. And similarly speaking, if you have a function that only produces the number 5 or 10, instead of saying nat, it's more accurate to say any of 5, 10. So if you ever have those circumstances where there's only a small subset of possible outputs, you should always give your contract with respect to them, because otherwise your user is not going to quite understand the behavior of the function. I realize this gets complicated. You have to remember that that contract and that purpose and those examples, because Racket is dynamically typed, that information that you've written in the comments is really the only information the user has. And you have to give them everything so that if they screw it up, it's their fault, not yours. All right. So, we've been talking about filter, which is an abstract list function, which, by the way, has friends. Filter's friends are map, fold, L, fold, R, and build list, and we will be talking about them probably next class. They're super awesome. And if you've ever heard of MapReduce, yeah, we have that. So, let's look at filter. What is the contract of filter? Now you know filter takes two things. It takes a predicate, and it takes a list, and it produces a list. But filter is an abstract function. You pass it any predicate and any list, and it produces a list. So it is very tempting then to write the contract of filter as a predicate that consumes any and produces bool. A list of any produces a list of any. This isn't right. This is not accurate. Certainly, we could use filter in this way. For example, if I wanted to do that there, this is any to bool, and this is a list of any. But it doesn't match the return type, because what's produced by this is not a list of any. It's going to be a list of lists, which technically a list is anything, so it's still very tempting to make this work, but here's the problem. If I say list of a Boolean function or a predicate takes any and produces bool, and I have a list of any, well, what if I'm trying to identify those items in the list that are even? So my predicate is even. Even consumes a number and produces bool. And it can only be run on numbers. And so my list that I pass to filter must only contain numbers or it will produce an error. So this contract isn't accurate because it hasn't captured the fact that the predicate's type needs to match the type of the list that's consumed. So we've got to solve this. It's actually pretty easy to solve. We introduce this thing called a type variable. And what's going to happen is I want to reflect the fact that the predicate needs to consume something that has the same type as the contents of the list. And the list that is produced by the function has the same type of thing that the input list had. So instead of saying any, which can literally mean anything, I'm going to use x. And x could be integer, and x could be nat, and x could be any. But we are maintaining the relationship that the predicate's type needs to match the list type. And if we just say any, they don't match, because any could be anything. This could be nat, and this could be strings. And that's totally valid. But if I use a type variable, and this is how we do it here, I am clarifying that the type of this predicate needs to match this type here, and the type of the thing that's produced would match as well. So this is much more clear. Now, what's interesting is that the contract on the previous slide is actually contained in here, because I can say x is any. But I'm also now being much more clear about saying that if this is a list of numbers, that this predicate must also consume numbers, and this must be a list of numbers. So it's just a more precise way of doing it. All right. Now, the term we use for this is generic or polymorphic because we are actually saying, okay, this function can be applied to many types. It is a generic function. And if you want to be a really great programmer and write code that is super useful, you want to write generic programs. And that is a challenging thing to do. And you can do it in languages like C and C++. It's a lot harder to do in C. In C++, we usually use a lot of templating, which is kind of like type variables. The template system is a pain, but it works. Yeah, it's fun. Now, just as a word of warning, filter only required one type variable. But it is very plausible that you can write other abstract functions that will require more than one type variable. We usually start with type variable x, and if we need a second one, we'll introduce y, and if we need a third one, we'll use z, and if we run out, maybe we can start all over again at a. I don't think we need that many. Any questions about this? All right. So, one last bit to this module. Sorry, I should note, if you see me skipping slides, it's not because I'm ignoring them, it's because I've already talked about them. I don't like this whole reading the slide business. One last thing I want to do. This is a cool thing. So, there's a couple different ways you have seen so far to represent data. You can represent data in lists, that is compound data, as a list. Very easy to do. Problem is that you start throwing around these firsts, rests, seconds, thirds, and so you have to write all these wrapper functions to wrap the list functions so that you can get the right element of the list for each field of instruction. So instead, we introduced define struct, which actually lets you have named fields. And it produced a constructor and a predicate to say, hey, this is this thing you want. It's pretty nice, right? And it also gave you those selector functions. So we have define struct. And here we have an example for a point. So this is a plain old point in two space, so just x and y. And you know that when you call define struct, you get a constructor make point, and you get a selector point x and a selector point y, and you get a predicate point question mark. One more way of simulating structures now. So you can do it with lists. You can do it even better with abstraction and with you treating functions as first-class values. So we are going to make the constructor. And we're going to call it nk point, so make point. And if you look at make point, we're simulating the constructor here, it consumes the field x and the field y, so those are our x and y coordinates. And then inside of make point, we have a local, and what this local does is it contains the definition of a function called symbol to value. And symbol to value consumes a single argument s, and that's a symbol. And if the symbol is x, we produce the x value. If the symbol is y, we produce the y value. And then the expression body of the local is actually just the function. What is this doing? Okay. Let's take a close look at what it's doing. So I'm going to define point 1 as being make point 34. So let's actually trace through this. So since make point 34 is an expression, I need to evaluate it and turn it into a value in order to bind it. So I'm going to substitute 3 and 4 into the body of make a point. And when I do that, I replace each x with 3 and each y with 4. And so now I have P1 is defined as this local. Well, P1 is still not being bound to a value, so I need to evaluate that local. So, of course, what are we going to do? We are going to rename symbol to value with a new unique name, lift that whole function out to the global scope, and everywhere where I have used symbol to value, I'm going to rename it symbol to value 38, and then I drop the local syntax. So I'm going to go from that step there to this step here, where I have this renamed global function symbol to value, and now P1 is assigned to symbol to value 38. Well, the function is a value, so this evaluation is actually done. What that means is that my point is a function. What does that mean, though? Well, so what do we want to do when we have a structure? Do you remember that when you have a structure, we actually consider the constructor with each of the field arguments as values to be the value of the structure? We just did the same thing. And if I apply that structure, because it's a function that consumes a symbol, so if I pass it the symbol x, it gives me 3. It's the selectors. And if I pass it the symbol y, it gives me 4. So make point produced a function with the fields embedded in that function. The values of the fields are embedded in that function. And then when I call that function and pass it the symbol that corresponds to the field, it gives me the field value. Now, of course, you don't want your users to have to know what the symbols are for each of the fields. That's silly. So then what you're going to do is you're going to write wrappers for the selectors. So you'll say point xp, you apply p and the symbol x. So you'll write these wrapper functions for the selectors, and now you have the constructor and you have the two selectors. You've just essentially simulated structures. It's kind of cool, I think. All right. One last thing to mention about this. So you made a point P1 that had x3 and y4. What happens if I then bind P2 to x equals 0 and y equals 0? What happens to P1? Does it change? And the answer is no. Because each time you bind a name to make point with some arguments, it gets bound to a brand new function. with those field values captured inside. So each time you call make point, you are getting a new copy of the function with your field values. So there's no overlap. You don't have to worry about the previous points changing values and so on. All right. Any questions about that? All right then. We are officially done with Module 13. Which means I can finally close it on my computer. And hopefully I won't bring your exam up. There's a good chance of that. All right, so there we go. We are now on to Module 14. And we finally get to do something super exciting, one of my favorite things. All right. So we've been talking about abstraction as being a really, really good thing because it is a really, really good thing. We take a whole bunch of functions that essentially do the same thing, and instead of having separate implementations, we give a singular implementation and we parameterize the operator we need. Super useful. Reduces code, increases maintainability, code reusability, it's great. But we are missing one piece of this puzzle. And let's see that piece. So if we look at our original implementation of our little function factory makeAdder, it has this local inside where we define f of m to be n plus m, and then that produces an f. Now what's interesting is that makeAdder produces a function. What's the name of that function? By what name do you call it? You don't know, because it doesn't have a name. Yes, if we were actually evaluating this, it would have a unique name, but you don't know what that name is, and you therefore can't use it. So this is an anonymous function. It has no name. Okay. If we want to assign that anonymous function a name, by the way, what we're going to have to do is bind it to a name. All right. So here's another example. So makeAdder that used a local, and we saw that the local produced an unnamed function. Now I want to go back to eat apples. So in order to implement eat apples, we originally had this simple recursive function that searches the list and removes the selective elements. Now we can just call filter. Filter requires a predicate. The predicate is to check, is this thing not an apple? Because if it's not an apple, I want to keep it. All right, so I need to define that predicate. That's not a predefined predicate, so I'm going to write a function called notSymbolApple, and I put it at the top level scope. I don't know why you did that though. Who is going to use this function, notSymbolApple? The only place that this was realistically going to be used was by filter. So you just cluttered up the top level space, and you gave your user a function you probably don't want them to use, or even know exists. Okay, you know the obvious answer. Put it in a local, right? So we put it in a local here. There we go, done, right? Yeah, but even if I internalized the definition of notSymbolApple, I still have to come up with a name for it. And I still, the problem I have here is that notSymbolApple is actually available for the whole body of eat apples to use. There's only one place where notSymbolApple is going to be used, and that is as the predicate to filter. So while I could put the local there, there's a better place for it, which would make notSymbolApple only available to the exact place it needs to be, which is as the predicate for filter. Yes, this is a little ugly. So now, because I can use a local to produce a function, I can put the local as the predicate and it produces that function. This is really ugly. This is nasty looking. You've got all this local, you've got to define there. And you know what my problem is? For this function that is technically unnamed, it's anonymous outside of that local, I still have to come up with a name for the damn thing inside the local. And because we want to be good developers, we want to come up with a meaningful name that doesn't clash with anything else to make our code readable. So I've still got to come up with a name for it. I just don't like it. This is really ugly. And I'm lazy. So this is another way we can do it. That local, which produced an unnamed function, was essentially equivalent to this magical thing called lambda. Lambda makes a function, an anonymous function. So you say lambda, and you pass it the list of arguments, and there's the expression of the function. That's it. Makes a function. No name. It's great. I love lambda. So why is this called lambda? We'll see in a minute. All right. So you want to see why we like lambda? Because you take that ugly crap and you turn it into that piece of beautiful work. I only need this unnamed function to be my predicate, so I just do lambda item, not symbol equal to apple, done. That whole function is 2 lines. I haven't exposed anything to the top level, so the user can't get in trouble. I also didn't have to come up with a nice, meaningful name, because I didn't need anything with a name. It's a single-use function. Beautiful. Yeah. Assignment 9? You don't have an assignment 10, by the way. Yeah.
What if we need to use 2 unnamed functions?
2 unnamed functions. Like one inside another one? Yeah, you can do that. You can put a lambda inside a lambda. I do it all the time, actually. And I can put a filter inside a lambda and a lambda inside the filter. You can put them wherever you need a function. Anywhere where you need a function, you can put a lambda because it makes a function. Yeah?
What's the difference between having that and just having, like, writing the function by the
So a predicate requires that you have an argument. So if I just put the body, which is just this, what's item? I need a way of passing the first or the current item that filter's working on into my predicate. So this actually has to be a function. What filter does, by the way, you've seen the implementation, it's going to apply the predicate to the first of the list, and then keep it if it's true, otherwise it removes it. So you actually have to be able to pass an argument into the predicate, which is why we can't just have body. All right. If you haven't guessed this, by the way, I really love lambdas. Where do they come from? So this is not some weird CS person who decided, hey, let's call this anonymous crap lambda because I like the symbol lambda. No, actually there's a reason for it being called lambda. And it actually has to do with functional programming. So if you actually look at the mathematical logic behind a functional language, there is a formal system of mathematical logic for it. It's called Lambda Calculus. And it's a bunch of unnamed functions. For example, it looks like this. That is a function. Actually, I think that might be false in Lambda Calculus. And I think that's I haven't done Lambda Calculus thread in a long time. This is where the name comes from. These are anonymous functions. Now, an interesting thing about this Lambda Calculus is, you know all those substitution rules? This is where they come from. This is what they're based on, is the substitution rules that are used in Lambda Calculus. Now, are they a one-to-one mapping? Not exactly, but they are based off of this Lambda Calculus. And if this is something that interests you, sit in on 145, because they do a little bit of it. But if you were like, really into languages and you really want to know what Lambda Calculus is, there's a 4th-year course called 442, and you will actually learn it. It's a really good course, actually. You'll do Scheme and ML and Haskell and a whole bunch of other lovely obscure languages. And it was really cool. So when I took the course, admittedly it was a long time ago, but we actually wrote interpreters for the previous language and the next one. So we wrote like a Lambda Calculus interpreter in Scheme, and then I think we did a Scheme interpreter in ML and Haskell. And then we didn't do that in Prolog, then we did an unlambda interpreter in Prolog. Unlambda, by the way, is an obfuscated functional language. You can look it up, but I warned you. It doesn't make any sense. It's just a bunch of S's and K's and things like that. It's obfuscated, which means a human can't actually read it. It's a fun course anyway, so if this stuff interests you, I highly recommend that course. But anyways, that's where the name Lambda actually comes from. And now we should go back and make adder look all pretty. Because it had that local that produced a function. I don't need the local anymore, I'll just put the lambda there. I went from 3 lines of ugly to 2 lines of awesome. It's great, I love it. All right. Now on to some dark secrets of the Racket language. So you've seen defined used in a couple different ways. You know that you can bind a name to a value. So define, interest rate, some value. And that value can in itself be a function. You can totally do that. So that's how you are going to either define a constant or alias a function. That is, bind a name to a function that exists. Or you can create a function by saying define, and then in brackets the name of the function, the list of arguments, and then the body. This is a lie. It's pure syntactic sugar provided to you so that you don't have to know about the existence of lambda until we want to tell you it exists. Because the first thing Racket does when it sees your function definitions that you've done all throughout this course is it converts it to this. It's going to define, name, and bind it to an anonymous function as a lambda. And I have been writing scheme code since the winter term of 2002. So a very, very long time I've been writing code in this language. This is only the second time I've taught this course, though. The first time I taught this course, I saw this first way of defining a function, and I thought the slides were full of errors. I had never seen it before. The only way I had ever seen a function defined is this way. And so as I'm writing my first assignments for 135, I'm doing it in the way that Scheme does it, which is the normal way to me. And everyone was looking at me and shaking their heads. I did not realize the first time I taught this course, well, in the prep leading up to it, that Racket had this syntactic sugar to hide the lambda from you. But that doesn't change the fact the lambda is still there, you just can't see it. And by the way, you can totally define functions like this. Racket just doesn't need to translate. All right. So does that mean your substitution rules have to change for functions? No. So if we present to you the function in the traditional form that Racket has, the syntactic sugar, you do not have to translate it to this first. So you can use, if the function is defined the way it would normally be defined for this course, go ahead as normal. However, if we give you this proper function definition, then you would be expected to do it properly. But you know how this is. There's no new rules here. There's absolutely no new rules to do this. We have bound a name to a function. It's the same as everything we've ever done. So, to show you that, let's trace through make adder defined properly without the syntactic sugar. All right. That means that we have define identifier make adder lambda x, and then remember when I said you can have a lambda inside a lambda? There we go, lambda inside a lambda. We have them all the time, it's normal. Then we have lambda y. So the internal lambda is the function we're producing, and the external one is the actual make adder function. Okay, so I want to apply make a 3 to make adder, and then to the function produced by that, we'll apply 4. So how do we actually trace through that? All right. Well, how would we normally trace through this? Make adder is a constant. It is bound to a function. So the first thing that I'm going to need to do, of course, is substitute the value of the constant for its name. So I replace make adder with lambda x, lambda y, plus xy. That's the first thing that you're going to do. And then, after that, in the next step, we see, oh, here is a value being applied to this unnamed function. It's the same rules as normal. Now the function just doesn't have a damn name. So I'm going to substitute the 3 in for all the x's, drop the lambda syntax, and shove up the body. So I replace 3 for x, and there's the body of that exterior lambda. All right. So now I have that internal function, or that external one evaluated, and now I'm going to apply 4 to that one. And so I substitute the 4 in for the y, and then I replace this whole thing with the body, which is just 3 plus 4. It's the exact same rules you've already been using, it's just now the functions don't have a name. That's it. Does it get a little confusing? Yes. Are we going to be jerks about it and reuse the same parameter names over and over again to try to trick you? Yes. You can ask Zara at the back about my tricks. She knows all about them.
I'm just here to study operating systems.
All right. So, there are some differences, obviously, between the syntax of these two implementations. And again, just to reiterate, the part of translating the syntactic sugar definition that you've always used into the lambda, that's not required. The only time where you're expected to actually use those lambdas is when we've actually explicitly used them. Otherwise, your functions can just go on as they normally would. And if you're wondering, this idea of syntactic sugar, is this a common thing? You're damn right it is. It exists in pretty much every language there is. For example, if you've ever done something in like C or Java in arrays and they've got those nice square brackets, that's syntactic sugar. You'll learn what it actually means in 136. All right, so, you know what? Let's end it there. I think the next slide would make a much better review than ending on it, so yeah. It's Thursday. Pretend it's Friday. Go home and try not to get sick. Oh yes, work on assignment 7. And assignment 8 will come out tomorrow.
I haven't started yet.
Yeah. The good news is there's only 9 assignments this term, right?